Swayam Prabha. Digital India. Educated India.
Today we will be looking at robot dynamics, and then after completing dynamics we will be looking at sensors and actuators. So, as we discussed in the last class, that robot dynamics essentially has to do with the relation between the force and the motion. So, if you look at our arm, then how this actually works is basically we have joints, and these joints are actuated by muscles. In the case of a robot, these joints are actuated by motors. So, when the joints are actuated, what happens? The arm moves, right. So, when the arm moves, there is a change in the position, velocity and acceleration at the joint. So, in our case we have joint here and 3 joints at the wrist. So, essentially dynamics has to do with the relation between the forces and the resultant motion for control of a robot, right. So, today we are going to look at robot dynamics, and as in the last class we looked at that there are essentially the study of robotics essentially has to do with forces and motion. So, we consider forces and motion, and depending on whether we are considering forces and motion or forces or motion, we study the study is divided into 4 groups. So, this is something we looked at we saw in the last class. So, this is basically no motion here and motion, and on the top side we have no force and force. So, this basically says that if our study is considering no motion then but only forces, then this is called statics. Okay. So, statics is basically the study of forces, what are the various forces which are acting on the joints due to an end effector force, and the system is not moving. So, it is basically a static system. So, this we saw that in terms of the Jacobian we can write this as the joint torques is equal to J transpose into F, where F is the end effector forces. So, this is called the study of statics. Now, next, if we do not have force, there is no force, but we only consider motion, then this is called kinematics. And this we also saw that kinematics is the relationship between the various joint velocities, the joint positions with the end effector position. So, essentially here we are looking at the forward kinematics and the inverse kinematics problem. Okay. So, kinematics is the study of motion without relation to forces. Now, when we are looking at force and motion, then this is what is called dynamics. Okay. So, dynamics is the study of force with relation to the position, velocity and acceleration of the joints. So, essentially what dynamics does is essentially what we are trying to see is if you are giving a particular joint torque, then the link is going to move. So, what is the relation between the joint torque and the link motion, and the reverse of that, if you want a particular kind of link motion, that means position, velocity, acceleration, then what is the joint torque that is required to get it. Okay. So, essentially it gives us the equation of motion for the robot arm. Now, this is interesting to note that what would come here when you are studying no forces and no motion. So, this is something interesting that what comes here. So, this is basically what we mean by styling, ergonomics, etc., etc. So, the other studies come in there. So, we have studied statics, we have covered kinematics, and now we are looking at dynamics. Now, in case of dynamics, basically we will be looking at the Lagrange Euler formulation. Lagrange Euler formulation of robot arm dynamics. Okay. And so, in this this is basically an energy based method, and we are looking at the kinetic energy, and the potential energy of the links, energy of all the links, and we form a Lagrangian. So, this is a scalar function called a Lagrangian, a scalar function L, which is a Lagrangian, which is taken as the difference between the kinetic energy minus the potential energy u. So, let me call this k, ki, and this is ui. Okay. So, we form this this Lagrangian, which is the difference between the kinetic energy and the potential energy for all the links. Then we sum it up and find it for the total system, and then we put it in the equation d dt of dl by d theta dot minus dl by dq by d theta is equal to the joint torque tau. This gives us the equation of motion. So, here theta is a generalized coordinate. So, theta is a generalized coordinate, and because we are talking of robotics, I have written theta, theta dot and theta dot, which is basically the joint angle for a revolute joint robot. But in general, please remember that theta is a generalized coordinate. Now, we see that the kinetic energy, so the kinetic energy is a function of theta and theta dot. So, basically what we are saying here is that the kinetic energy of the system is a function of, so let me write the kinetic energy. So, kinetic energy is a function of theta and theta dot. So, basically what we can do is, in our equation here, d dt of dl by d theta dot minus dl by d theta is equal to tau. I can say that my L, where L is equal to kinetic minus potential energy, and this kinetic energy is a function of theta and theta dot. So, what we can do is I can open it up. I am writing this this L in here now, and we can open it up and write this equation as d dt of dk by d theta dot, okay, minus dk by d theta plus du by d theta. This is easier to write, this is easier to work out when we are doing our problems. Okay. So, what we have done here is that we see that the Lagrangian L is a scalar function of the kinetic energy and the potential energy. The kinetic energy contains theta and theta dot, and the potential energy only contains theta. So, what we do is, when we put it in, when we put this this equation in here in terms of L and open this, now what we get is this equation. So, here what you can see is that kinetic energy is being differentiated with respect to theta dot and with respect to theta, but the potential energy is being differentiated only with respect to theta. So, this is the equation that we are going to use. So, this is our equation 1, and this is the equation that we are going to use when we derive the equation of motion and the joint torques for a robot manipulator. So, let us have a look at an example. So, this is an example which we are trying to solve here. So, this is an example. Now, let us see this example, how we can derive the torques. So, essentially this is a robot manipulator. So, this manipulator is 2 degrees of freedom. So, 2 degrees of freedom, and it has one revolute joint and it has a prismatic joint. Okay. So, my revolute joint is this joint, which is rotating here, which has an angle theta 1. Let us say the mass is concentrated, m1 is concentrated at the CG, and this distance here from here to here is L1, and the link 2 has the mass which is concentrated here, and this is my m2, and let us say my distance from here to here is t2. Okay. And gravity is acting in this direction. Okay. So, the first thing to do is to understand how this manipulator moves. It is 2 degrees of freedom, it has one revolute joint and a prismatic joint. So, the first joint is revolute and the second joint is prismatic. So, if I have my arm like this and if the same manipulator is there, if this is revolute joint, this can move like this, but this fellow is prismatic, so it can move, it can slide in and out of from here. So, essentially this is what the structure of the manipulator given here looks like. Now, when it moves, what moves, let us see and be very careful, be very clear about that. So, when the first joint is rotating, when theta 1 is moving, what would happen is this link is going to move like this. Okay. Now, because this link is moving in this way, this fellow will also have a velocity. That is something we saw in the last class. Okay. So, the first degree of freedom is here, the second degree of freedom is here. Okay. So, this is my second degree of freedom, which is my d2. Okay. Now, let us try and derive the equation of motion of this. And now, the other parameters which are required are, let me write another thing to note is the direction of g. So, let us say g is in this direction. The other parameter which is required is the inertia tensor, which we write it as Ixx 0 0, then 0 I y y 0 0 0 I ZZ. So, this is my inertia tensor, and we can add the subscript 1 indicating it is for link 1. Okay. The inertia tensor for link 2 is almost similar. It is Ixx 0 0 0 Iyy 0 and then 0 0 Izz. So, this is link subscript 2 to indicate this is for. Now, note that the robot is going to rotate about the z axis. Okay. So, the z axis is in pointing out of the board, okay, or of this sheet of paper. So, when the rotation takes place, it takes place about this axis. Now the z axis about here is about here. Okay. So, that is my z, it is rotating, it is moving along the z axis here. So, essentially it is going to be this term and this term which is going to come into effect, the Izz about the z axis always. So, let us proceed. So, the first thing that we need to do is we need to write our for link 1, let us write the kinetic energies. So, the first we find out the kinetic energies for link 1 and link 2. So, K1 for link 1 is half m m1 L1 theta 1 dot squared plus half I ZZ1 into theta 1 dot squared. Okay. So, this is the kinetic energy for link 1 and the kinetic energy for link 2. So, this is very easy. So, this term is essentially coming from half m v squared. So, this term is coming from v squared, which is equal to v is equal to omega r, right, squared. So, omega is equal to theta r. So, you can see that it is theta r squared. Okay. That is where it is coming from, right. So, this is how we have half m v squared plus half omega I omega, that is where your this term is coming from. Okay. So, we have two terms, kinetic energy of the first link is equal to half m v squared, v is equal to this, and half omega I omega, which is giving me this term. The second term is for the second link. Now, something to note here in the second link is that when the second link moves, this is getting effect, this will have a component which is d2 dot here. Okay. So, d2 dot is the linear velocity of this link which is moving. Okay. But we also have to note that when theta 1 moves, what is happening is this fellow, because theta 1 is moving here. So, theta 1 dot is there, what will happen, this will have a linear velocity component also, this will have a velocity component also, because theta 1 is affecting this link number 2 also. So, when we write kinetic energy for the second link, what we are going to write it as is half m2. So, m2 is getting affected by the theta 1 dot which is here. So, we are going to write this as d2 d2 squared theta 1 dot squared half m v squared, and so this is half m v squared plus its own velocity d2 dot, okay, plus the half I ZZ2 theta 1 dot squared. Okay. So, let me explain again that this component is essentially because although this is link 2 and it has a mass 2 here at this point, but because this is also rotating, it is translating and also rotating because there is a rotating velocity here. So, this component will come plus its own linear component which is given by d2 dot. Okay. So, we get one component here because of the rotation and which is being added to the linear component which is d2 dot, plus this is my component which is coming from here. Okay. So, now this is the kinetic energy and this is the half m v squared. So, there is going to be a squared term here, right. So, this is our kinetic energy plus the potential energy. So, the total K1 plus K2 is equal to half, I just take the sum of this which is equal to m1 L1 squared. So, I take theta dot squared common. So, there is a theta dot here, there is a theta dot here and there is theta dot there. So, I take L1 m1 L1 squared plus Izz 1 plus Izz 2 plus m2 d2 dot squared, and my out here is theta 1 dot squared. Okay. So, what we have got is I have collected all the terms which have so this is going to be d2 squared m2 d2, this does not have a dot. Okay. So, this is all terms having theta 1 dot squared. So, there is theta 1 dot here, theta 1 dot here, theta 1 dot here, and there is a theta 1 dot here. So, there are 4 terms plus the term which has been left out is this d2 dot. So, I am going to write the other term separately, half m2, and it is d2 dot squared. Okay. So, that says that the kinetic energy is a function of the velocity here, okay, which is my theta 1 dot squared, and it has a function of the linear velocity d2 dot squared here. Okay. So, this is our kinetic energy. Now, next is our potential energy. How do we compute our potential energy? Essentially, the potential energy U. Let us go back to the figure again and see that the potential energy of this is going to be mg is going to act downward. So, that is my mg. L1 is the length, plus if I say an angle theta, if I take this as the reference, let me take that as my reference 0, then this is my angle theta. Okay. So, it is mgl sin theta is the height by which this has moved up. So, essentially my term u1 is going to be m1 L1 g sin theta 1, plus we add a reference term which is called the reference m1 L1 g. So, this is what is called the reference term. So, this is my reference term. Okay. So, the kinetic energy of the first link is equal to the mass into the gravity which is acting downward. So, this will give me a force in this direction. The height by which it has moved up would be mg will be L sin theta, if provided this is my theta. Okay. This is my theta reference. So, that is how we get our first term, which is m1 L1 g sin theta 1, plus the second term that we are getting here is essentially a reference term. What this means is that if you see carefully at this figure, that here is my 0 reference. So, although I am saying this is my 0 reference, this is actually not the 0, because gravity is acting in this direction, right, it is acting downward. So, if the manipulator comes here, the energy is actually not 0. Why? Because if I leave it there, if you can imagine, this will immediately come down and fall. Okay. It is like my arm. So, let me explain the concept of the 0 reference again, that if you have an arm like this and I say this is my 0 reference. Okay. So, here I am saying this is my 0 reference. So, whatever is going up is my angle theta. So, its sin theta is the height there, but this is actually not 0, because if it has some potential energy here, what this means is that if I switch off the actuators, the arm will immediately fall down. Why? Because gravity is acting in the downward direction. So, I need a reference potential reference which is going to hold the arm here, okay. And that is my potential energy reference, which is mg m1 L1 g, because my reference was taken at the horizontal. Okay. So, this is to explain what is the meaning and the need for this reference term. So, this is the potential energy of the first link. The potential energy of the second link is again we can have a look at this. So, potential energy of the second link is going to be so this is my mass 2, this is going to be moving in this direction. Okay. Now, because this fellow this theta is moving, there is an angle theta. So, the component of theta also will be there. So, it is m2 d2 similar to this g sin theta 1. Okay. So, theta 1 is the angle. So, if you note here again, as soon as this theta 1 changes, what will happen? This potential of the second link will also change. Okay. So, the potential energy depends on this theta 1 of the second link also, m2 d2 g sin theta 1, plus it has a reference which is m2 g d2 max. Okay. The same logic of having the reference term. The only difference here being that this d2 that we are seeing here is a translating joint. So, the length of d2 is going to change. So, we are taking it as d2 max, the maximum length to which it can go, and we are writing this as d2 max. Okay. So, this is the reference for the first term, and this is the reference for the second link. Now, if we add both of them, then what we get is u of theta, so is equal to u1 plus u2, and this is equal to there is sin theta common. So, I am going to take sin theta common, and g is common. So, I am going to write g m1 L1 plus m2 d2. Okay. G I have taken out, and sin theta is here, sin theta 1, plus the reference fellows m1 L1 g plus m2 g d2 max. Okay. So, something to note here is that this is not a variable, this is a constant term, this is also not a variable, this is also a constant term. Okay. So, we have potential energy and kinetic energy. So, let us now use our equation that we saw earlier, equation 1 that I wrote here. So, it is d dt of the kinetic energy with respect to theta dot. So, I am going to differentiate first with respect to theta dot. which is the velocity. Then I am going to differentiate the kinetic energy with respect to theta, and then I will differentiate the potential energy with respect to theta. Okay. So, we have written it in this form, so that it becomes easier to do the differentiation and then to understand which term is going where. Okay. So, here let us start off with our, so let us take a new page. So, here what we are saying is dk. So, first differentiation is dk with respect to d theta dot, sorry, this is my velocity here. So, differentiation of this with respect to d theta dot. So, kinetic energy differentiating with respect to my velocity. So, if you look at the expression of kinetic energy again, this is kinetic energy and this is my d dot theta 1 dot. So, it is differentiating with respect to theta 1 dot, and there are two variables. So, theta 1 dot is one variable and d 2 dot is the other variable. So, first I will differentiate with respect to theta 1 dot, then I will differentiate with respect to theta 2 dot, and what we get here is this is being written in matrix form. So, m1 L1 squared plus I z z1 plus I z z2 plus m2 d2 squared, this is going to become my theta 1 dot, and the second term is m2 d2. Okay. So, here I am differentiating with respect to theta 1 dot, and here I have differentiated with respect to d2 dot. Okay. So, this will be d2. So, let us look at this expression again. Okay. So, we have our kinetic energy here, we have differentiated first with respect to theta 1 dot, then I have differentiated with respect to theta d2 dot. Okay. So, this is our kinetic energy term. Next, I am going to differentiate with respect to, so the next term is going to be my dk by d theta. Okay, the kinetic energy with respect to theta. Now, when we go back here and see the kinetic energy with respect to theta, there is no theta here, it is only theta dot. Okay, so, we can't differentiate with respect to theta dot theta. So, this will become 0. Okay. So, the next term that we are going to differentiate is with respect to, we are going to differentiate with respect to the first term we are differentiating with respect to theta 1 dot, and what we get is we get 0 here. And the second term what we are getting is there is a d2 here. Okay. So, there is a d2 here, where is the d2 gone? There is a d2 here. So, we are differentiating with respect to d2 here, and what we are getting the second term here as m2 d2 theta 1 dot square. So, we are getting this term as our second term. Okay. So, we have got the two terms of dk by d theta, dk by d theta dot. Now, what we need is the third term, which is the third term, which is du by the third term is du, sorry, du by d theta, which I am writing as. Now, let us look at the term expression for u again. The expression for u is given here. So, the variable is theta 1 is there, plus there is a d there, right. So, we have a d and theta 1 both there. So, I am going to differentiate first with respect to first with respect to theta. What we are going to get, m is m1 L1 plus m2 d2 into cos theta. Okay, sin theta becomes cos theta 1, and the second term is going to become g m2 sin of theta 1. Okay. So, we get two terms here. First fellow I differentiated with respect to theta 1, then I differentiated with respect to d. Then here also we differentiated with respect to theta 1 dot, and then we differentiated with respect to theta 2 dot. Okay. So, the three terms that we are getting is given by this is number 1, this is number 2, and this is number 3. Okay. So, we have derived our. Now, what we need to do is to put it in this equation number 1 again. So, this is my equation number 1, which means that I have got this term, I have also got this term. What I need to do is take d dt of dk by d theta dot. So, let me write it again. Okay. So, let me write it again, d dt of just to maintain the consistency with what I had written before. So, what we do now is I need to take the d dt of this term here now, d dt of this term, okay, to complete the derivation. So, now if you look at this term, what we see is that d dt of this, that means derivative of this with respect to time. So, this is my d dt of, okay. So, now if you look here is that we find that there is a velocity theta 1 dot, which is a variable, and d 2 is there, which is also a variable, and in the first in the top row. In the second row we have d 2, which is a variable here, right. So, now if you take d 2 dot, then what will we get is, so what we need to do now is take the derivative with respect to d 2 dot, and what we get here is our equations for torque 1. So, torque 1 is equal to m 1 L 1 squared plus I z z 1 plus I z z 2 plus m 2 d 2 squared divided by theta 1 double dot, theta 1 double dot plus twice m 2 d 2 theta 1 dot d 2 dot plus this term m 1 L 1 plus m 2 d 2 into g into sin theta cos theta 1. Okay. So, our first torque at the first joint, now we see that has a term which is proportional. This is something like the inertia term, this is acceleration. It also has the Coriolis and Coriolis term, that is this one, which is theta 1 dot into d 2 dot, and this is my gravity term, which is in terms of gravity, right. So, the first joint of the manipulator, if you see, is affected by the acceleration of the first joint, that is theta 1 dot. It is also affected by the gravity component, which is coming here, plus the Coriolis component. Now, why does the Coriolis component and Coriolis centrifugal component come? Essentially because this is rotating and this is translating on this object, right. So, on the link number 1, link number 2 is translating on a rotating link, and because of which we get this second term here, this term here, which has theta 1 dot and d 2 dot. Okay. Now, what about link number 2? In link number 2, what we do get is m 2 d 2 double dot minus m 2 d 2 into theta 1 dot squared plus m 2 g sin theta 1. Okay. So, here what we are seeing is that we are getting the term d 2 double dot plus theta 1 dot squared plus sin theta 1. Okay. Now, if I write it in matrix form, this is for link 1, this is for link 2. If I write it in matrix form, then I can write it as m of theta, the inertia terms. What we do is I am going to bring the terms which are responsible for inertia, that is this, okay, and write it as m 1 L 1 squared plus I z z 1 plus I z z 2 plus m 2 d 2 squared. This term is 0, this is 0, and this is m 2. So, we can see that m 2 is here, okay, and this is my this term here. Okay. So, this is the something like the inertia matrix, and this is the inertia term. The next term that we are going to put together are terms which are combined with theta and theta dot. Okay. They are the centrifugal and Coriolis terms. So, this is my second term, which is v theta and theta dot. These terms depend on theta and theta dot, and this comes out to be twice m 2 d 2 theta 1 dot and d 2 dot. And here we are getting minus m 2 d 2 theta 1 dot squared. Okay. So, here we are getting two terms which depend on theta and theta 1 and theta dot. Okay. So, this is my Coriolis and centrifugal forces, Coriolis plus centrifugal force, centrifugal forces. This essentially is my inertia forces, inertia. Okay. And the last one, that is here, what is left is terms which are with respect to g. Okay. So, whatever term is there with respect to g, then those are the terms that we collect together and we write them as a gravity matrix g theta, which comes out to be m 1 m L 1 plus m2 d2 into g into cos theta, and this is m2 g into sin theta 1. Okay. So, this is what we call a gravity term. So, the total dynamic equation torque, if we write it like this, is equal to the inertia term, which I can write as the inertia matrix D into theta double dot. Okay. Now, so I can write it like this, plus a term which is proportional to V theta into theta dot. This is my Coriolis plus centrifugal forces, plus we have another term which is my gravity term, which I have written as g of theta. So, this is my gravity term. Okay. So, the total torque acting at a joint is a result of the inertia torque, which is Coriolis and centrifugal torque, or the component torque because of Coriolis and centrifugal forces, and then the torque because of gravity. Now, if a manipulator is moving very fast, so essentially what we have seen is that our joint torques are have three components, or is because of the sum of three parts. The first part is because of inertia, because the link has inertia tensor. So, when it is moving, there is going to be inertia loading on the joint. The second is Coriolis centrifugal. Now, Coriolis centrifugal essentially comes because if you can look at the arm, so we have one link and there is another link. So, there is one link which is moving on a rotating link. So, there is a rotating body on another rotating body, and because of which the Coriolis and centrifugal forces come. And the third is the gravity component, that is because the link is moving up or down and the gravity loading is in the vertical direction. So, these three components make up the total gravity loading. Now, in terms of computation, this was a very simple example, but in terms of computation, if you look at the computation load, computation requirement, then or if I reverse the question, that out of these three, which are important, which are not important. Now, this gravity fellow does not depend on theta dot and theta double dot, that you can see. So, the gravity vector that we got here has only cos theta and sin theta. Okay. It does not have velocities or accelerations. That means that gravity loading will be there irrespective of how fast or how slow the system is moving. So, gravity loading does not depend on theta and theta dot and theta double dot. So, it means gravity loading will be there irrespective of whether the system is moving or is not moving. Now, Coriolis and centrifugal depend on position and velocities, and the inertia part depends only on the acceleration components. Okay. So, out of these components, this Coriolis and centrifugal forces are very, very small. They are less than 1% of total torque. Okay. Normally, for a normal system, the Coriolis and centrifugal component in the torque will be very, very small, but the computation time will be very, very large. Okay. So, the computation time will be large for computing the Coriolis and centrifugal force components. So, one way of doing fast computation is to neglect this part and neglect the Coriolis centrifugal component, because it is very, very small, okay, and only concentrate on the gravity and the inertia loading. Now, the inertia is if theta double dot is large, okay, that means the system is moving very fast, then acceleration will have a very large value, and if acceleration is large, you can see this is d into theta double dot. So, if theta double dot is large, then only this component will be large, otherwise it will be very small. So, if a system is moving very, very slowly, then we can get away by simply doing the computation for the gravity load and leave the others. Okay. So, gravity load will always be there, except if you are going to outer space. So, gravity loading will be constant, and it will be having a consistent load. So, this is constant load, constant loading. So, constant, let us call this load. The meaning of constant here is that it is present at all times. Okay. If accelerations are small, then this loading will not be there. For small theta double dot, again this loading will not be there. Okay. So, when we are trying to do fast computation, or we are trying to compute the dynamics, if a system is moving very fast, okay, then we add the inertia terms in the computation. If a system, gravity always has to be there. Now, the way of doing fast computation is essentially by using the inertia load and the gravity loading. So, essentially let me do it here, that this component is for if there is very fast motion, and this one is always present. Okay. This is very small and can be neglected. So, when we are doing dynamics of a system, it is important to note that what is the speed at which you are operating. So, if it is not very fast, then it is a good idea to not to worry too much about dynamic forces. So, this basically what we saw today is how to compute dynamics using Lagrangian Euler method, and essentially this is an energy based method in which we find the kinetic energy of the link, then we find the potential energy of the link, we construct a Lagrangian function by taking the difference of the kinetic energy and the potential energy, and then put it in the equation of motion and find the torques. Okay. So, this was done for a very simple example. If you go for higher systems, say 4 links, 5 links, then obviously it is not possible to do by hand. So, normally people would be using a computer program to write the dynamic equations and then try and solve. Okay. So, we will not go further here. This is enough to understand the dynamic equations, and we are not going to go beyond this here. So, the next topic that we need to see is sensors and actuators. So, we have seen that a robot essentially moves by or the robot links move by actuating the joints, and the joints are connected to motors. Okay. And these motors are actuators of some kind, and where the link is in space depends on this feedback is given by the sensors. Okay. So, suppose my arm is here, basically to move it I need to give joint torque. So, the arm moves. Now, where is the end effector is told can be found from the joint angles. Now, this joint angle is found by sensors. So, each of the joints would be having a pair of motors and sensors which are going to give the actuation and is going to give the feedback. So, the next topic we are going to look at is sensors and actuators. Okay. So, sensor actuators are essentially for providing the actuation or for providing energy to move or forces to move the system, and sensors are essentially for feedback of where the end effector is, Okay. So, next we need to move on to sensors and actuators. We will start off with this basic diagram here, which basically gives us which explains the various components in a control system. So, in a basic control system we have 4 parts, and so one is going to be the controller, which is basically going to control the system. So, this can be a microcontroller, or a microprocessor. Then we have an actuator. So, this is my actuator, okay, which is going to actuate the system, which is going to move the system. Then we have the link actually. So, this is my link which is actually moving, and this is my feedback sensor which is giving the position feedback. So, how does this work? Suppose we want to move this by 10 units, just for example. Suppose I want to move it by 10 units in the x direction. So, this input value is going to be 10 here, okay, to the controller, and what the controller would do is it is going to take the feedback from here and see what is the present position of the link. Now, suppose the present position of the link, just for example, is 0, it is at position 0, then it will do 10 minus 0 and create an error and say it is 10. Okay. So, what the controller does essentially, it produces an error of the the theta present to minus theta desired to theta present, okay, and this is going to be my error. Let us call it the error here. So, what the controller would do is it will see what is the desired value, it will see what is the present value and make a error, and then it will take the error and give it to the actuator. So, this will start moving. Now, when this is moving, what would happen is the position sensor would be saying that this is increasing now. It was 0, it is 1, 2, 3 like that. Okay. So, the feedback is coming from here, and the controller is continuously updating that feedback. So, it started off with 10 minus 0, then it will become 10 minus 1. So, it started with 10 minus 0, then it becomes 10 minus 1, like that it becomes 10 minus 8, and the moment it becomes 10 minus 10, it knows it has reached. Okay. So, the function of the controller is essentially to generate an error and make this error equal to 0. So, what does a controller do? It generates an error and then makes the error go towards 0. Okay. That is how a basic controller works. Now, let us look at the basic definitions of a controller, of a actuator, sensor, and the need for this feedback loop. Now, something to be noted very carefully here in this feedback diagram is that a microcontroller is basically electrical. So, it is an electrical device. Okay. Electrical device means it understands electrical signals, okay. Normally binary signals. Okay. So, it can only understand electrical signals now. So, it cannot understand a pneumatic signal or a hydraulic signal. Okay. Now, the controller understands electrical. So, what is coming back to the controller also has to be electrical, otherwise it can't do the comparison here, right. So, essentially what we are seeing in this diagram is that the actuator basically converts energy. This is my electrical energy, let us call it E. So, from electrical energy the motor rotates and it produces mechanical energy. Okay. So, this is mechanical energy or mechanical motion. The link is moving, which is mechanical energy, and what the sensor does is it converts mechanical energy back into electrical energy. Okay. So, in this loop is basically an energy conversion loop. So, we can call it as an energy conversion loop. Okay. What the actuator is doing? So, what the actuator is doing is it is converting energy. What kind of energy? In this case it is electrical to mechanical. What the sensor is doing, it is converting mechanical energy to electrical energy. Okay. And what the controller is doing, it is basically comparing. So, the controller is essentially a comparator which is seeing the desired value to the present value and is driving the actuator in that direction. Okay. So, this is the basic control systems loop for a robot control system. And so, there are 4 subsystems controller. So, we will look at microcontrollers after a few days, after a few lectures. Then we will look at actuators, sensors, and then the process and the process model, which is whether it is a robot or it is a industrial control or it is so the basic control system structure remains the same. So, we have seen that these are the 4 elements which are there, and the basic definition of sensors and actuators is energy conversion from one form to another. So, what does an actuator do? It basically converts, let me write the definitions of, this is the general definition. So, it converts electrical energy to mechanical energy. Okay. So, something moving is mechanical energy. So, electrical to mechanical conversion. What does the sensors do? It also converts. So, it converts electrical mechanical energy. So, energy to back to electrical energy. What does the controller do? It basically compares desired to present and creates an error, say let us call it del E, and this del E it makes it equal to 0 and drives it to become 0. Okay. System model of course gives us the basic motion of the system, what is the mass, what is the damping. System model will be made up of the mass properties, if there is damping in the system and there is friction, etc. Okay. So, this basic definition covers all sensors and actuators. They are basically energy conversion from one form to another. And so, a basic feedback control system would be having this 4 parts. Okay. Now, let us look at individually. We are going to study sensors, then we will look at actuators, then we will look at system models, then we will look at a little bit of control systems. So, let us look at the basic open loop and closed loop system. So, if there is no feedback and the system is just connected in series, so we have an input here and we have an output there and there is no feedback this way. So, this feedback is not there, then we say it is an open loop system. Now, in an open loop system there are advantages. For example, if you are using an actuator which is moving in open loop like a stepper motor. Okay. So, a stepper motor moves in steps. So, the stepper motor, because it is moving in steps, you do not need to have a feedback there. Every actuation would mean one step. And the advantage of using that is that it is much cheaper because it is an open loop. You do not need complicated controllers, etc. The other is the closed loop, where you have a controller, actuator, process, and you have a sensor feedback. So, this is my closed loop. Now, robots would generally be coming under this loop, okay, because we want very accurate control, and because of which we use this closed loop control system. Now, general sensors classification. So, we will start off with sensors. So, general sensors classification are of 2 types. The first is internal sensors. Okay. Now, the internal sensors are required for the basic working of the system. So, let me draw a robotic system here. Okay, this is my link. and at each joint we have a motor, we have a gear in front, and we have an encoder or position sensor at the back. Okay. So, every joint will be having one of this, and that is how it moves. So, there is a motor, there is an encoder at the back, and there is a gear sitting in front. So, how does it move? The motor is given a voltage, it moves, the angle changes, and because of the angle change the xy changes. Okay. Now, in order for the joint to for the motor to work, what you find here is that you need a sensor for position feedback, because it is operating in closed loop control. So, we need a feedback sensor here. Okay. So, there is a sensor which is required for the feedback control, and that is this one in the case of the robot system, which is an encoder. Now, without this internal encoder, the robot will never know where the position angle is, if this is my theta 2 and this is my theta 1. Okay. So, if I do not have an encoder there, there is no way for this robot to know what is theta 1 and theta 2. Okay. So, if I do not know what is theta 1 and theta 2, I will not know what is xy. So, xy, as you know, as what we have done so far, is a function of theta 1 theta 2 in this case. Okay. So, this feedback is given by my encoder of what is theta 1 and theta 2. So, such sensors that are required for the basic working of the system, okay, are called internal sensors. Without these internal sensors, the system will not work. Okay. An example of this internal sensors is the position sensor and encoder. Encoder also gives velocity and accelerations. Now, the robot may also need to interact with the environment. For example, if there is a wall here, just for example, there is a wall here and the robot should not hit that. So, what we can do is we can put some kind of a sensor here, okay, which is checking the distance, okay, or I put a camera. Now, this camera is basically seeing how far the wall is, okay, or if there is an obstacle, let us not say how far the wall is, or if there is an obstacle somewhere. So, the camera is basically detecting an obstacle, so the robot does not hit it. So, for external interaction with the environment, you require other sensors, for example, vision, force, touch, smell, okay, speech, etc. Right. So, external sensors are required for interaction with the environment, not for the internal working of the. So, this is a fundamental classification of sensors as internal sensors and external sensors. Internal sensors are required for the basic working, in this case it is an encoder. External sensors are for interaction with the environment, so something like vision, force, torque, touch, smell, speech, hearing, and all that. Okay. So, if any external sensor goes bad, then the robot can still work, but its interaction with the environment will come down. So, I hope this part is clear as what is internal sensor and external sensors. So, first let us look at internal sensors. So, we are trying to look at internal sensors first before we come to external sensors. Now, internal sensors basically give us position, velocity, and acceleration. So, when the robot is moving, okay, so this is my robot link, it is moving in space, from here it is coming here like this. Okay. So, I want to know what is the position here, what is the velocity, and what is the acceleration. I need to know position and velocity and acceleration, because you see the motor is going to rotate and the motor will have some velocity, will have some acceleration. Okay. So, at the end of the day I am trying to control x dot is equal to j into theta dot. So, the velocity of the motor is being used to control the velocity of the end effector. So, I need position, I need velocity, and I need acceleration. Now, the sensors which are most commonly used in for getting internal information is the potentiometers, encoders, LVDT, tachometers, accelerometers, and the sensors for interaction with the environment, which are external sensors. They are normally touch sensors, pressure, force, slip, proximity, vision. We also have maybe hearing, etc., etc. And these are basically ultrasonic sensors, force sensors, Hall effect, inductive, piezo, etc. And then finally, camera, the most important. Okay. So, these are sensors which are giving the external interaction with the environment. So, first let us start off with the position sensors. So, the first sensor, that this is something you would have studied in school in class 8 or 9, is a potentiometer, and how a potentiometer works is essentially shown in this figure, that we have a resistance coil here which is shown here. So, this is my resistance coil. Okay. So, this is a resistance coil, and there is a link which is moving, or there is a wiper which is moving, right. So, what we do is we take this the link and fix it to the wiper, or take the wiper and fix it to the link. So, when the wiper moves, what will happen is it is going to move from here to there, okay. And you can see that we give it a particular voltage. So, from this end to this end there is a voltage, and we find the ratio of the small r. So, if the wiper is here, then the resistance is the small r here. So, small r to the total resistance is capital R. So, basically I find the ratio of small r to capital R, and we do some kind of calibration. So, at this end, when the wiper is exactly here, we say that it is 0 degrees, and the wiper is exactly there, we say it is 180 degrees. Okay. And in between, wherever it is, I can look at the voltage, the R by R ratio versus theta, or the other way around, we can say this is my theta. For every change of theta, what is the small r by capital R ratio. So, theoretically it should be a straight line going from the something like that. Okay. So, we can first calibrate it, take it to one end, look at the voltage, okay, and then take it to the other end, look at the voltage. So, what you are going to get is essentially a voltage here, right. So, this ratio is actually a voltage. Now, so after doing the calibration, we get our calibration chart, and this calibration chart will tell us we can be used to get any unknown location for theta. Right. So, this is a rotating kind of potentiometer. We also have a linear potentiometer. Okay. Now, the linear potentiometer works exactly in the same way. So, we have a wiper which is here. Now, the wiper will move in this direction and this direction, and what would happen is the ratio, the small r from here to here, and the capital R is from here to here would change. So, we are again looking at the ratio R by R, which is actually a voltage. So, if I am applying say 10 volts on R, then if R is small r is not equal to capital R, then this voltage is going to vary. Okay. Again, we use a calibration, and we find what is the relationship between the position x, in this case it is position x versus voltage being produced. Okay. This is for a solid state type, in which we have a wiper and there is a thin film resistance here. So, exactly the same, I fix this to the link of the robot. When the robot link is moving, the wiper will move, and the ratio, if I say this is my total resistance R and this is my small resistance R, then if I give some input here, okay, that ratio is going to change, right. So, essentially this is how the potentiometer works. Now, we have some potentiometers here. You can have a look at the potentiometers. So, this is showing a potentiometer which is very, very small. These potentiometers are very, very small. You can have a look that this is the potentiometer. Okay. There are 3 outputs. So, in this figure also you can see that there are 3 outputs. There is one here, the 2 are for giving the supply. So, there is one here, there is one here, and there is another output here. Okay. So, these are the 3 output pins of the potentiometer. The potentiometer is when I rotate. So, I fix it to the link will be fitted here. So, if this is my link, I will fit the link onto the potentiometer, and when it rotates, you can see that the marker here is moving, right. So, when the link moves, the wiper is moving, and if I open the potentiometer, this is a closed potentiometer, it is very, very small. If I open it, I can open it into parts like this. Now, you can see more clearly, hopefully, that this is this part. So, when we are looking at the wiper inside, this is the wiper inside, okay, and this is the this is the resistance film inside. Okay, this is not the wiper. The wiper is this one on top. Okay. So, this wiper is the one that is moving on the resistance film, which is here. Okay. So, when it is contacting, it is like this. So, this is fitted onto the joint, and when it moves, the contact point between the wiper and that changes, and that is how the resistance, the ratio of the resistance changes and the output changes. So, this is a potentiometer which you would have used. The second kind of sensor, position sensor, which is very commonly used, is the potentiometer, and the working of the potentiometer is also very, very simple. So, we have a ring which is having slots in between. So, you can visualize this. So, the black parts are opaque, opaque is black, and the transparent parts are white. Okay. So, you can see this, right. Now, how this works is essentially, if I take the side view of this is rotating about that axis. So, if I draw the side view, so this is my side view, I hope you can imagine that. So, this is my side view, this is my axis. So, on one side So, this is my side view. Okay. So, on one side we have an emitter and on the other side we have a receiver. Okay. Now, this emitter is going to emit light. So, it will go like that. Now, the receiver is essentially a photocell which is going to receive that light. So, whenever this one has slots and opaque and transparent parts. So, whenever there is a transparent part coming in, the light will go through and you will get a signal here. Whenever the opaque part comes in, light cannot go through, so you will get no signal here. So, essentially it is like saying black 0 and 1, whenever it is transparent it is 1, light is going through, whenever it is opaque it is 0, light is not going through. Okay. And that is how essentially the potentiometer works, and this is an example of a potentiometer. So, you can have a look at the potentiometer. So, what you can see is this is a ring and there are holes in there, and there are so these are the slots that I just showed. So, there is an emitter and a receiver. So, there is an emitter on this side and there is a receiver on this side. Okay. So, the emitter is transmitting light, is giving out light, and the receiver is receiving the light. So, whenever we come to a hole, the light will go through and it will come to the receiver. So, it will get a 0 signal, it will get a 1 signal. So, whenever it is transparent, light is not going through, then the receiver will not receive anything. So, it is like 0. So, essentially we have connected it to LED here. You can see the LED blinking. So, when we are looking at the LED which is connected here is giving red light. So, essentially when I am moving the encoder, depending on whether it is light is going through or light is not going through, the LED will also be blinking in that order. So, this is essentially how the encoder works. So, fundamentally the encoder is a position sensing device and it works basically like this. Okay. So, working is very simple, and it basically gives the position feedback. So, if you know the distance between any two of these slots, okay, suppose it is 5 degrees, then the distance between any two blinks is also 5 degrees. So, that is how it understands what is the position of the shaft. Now, what is done is in industries we have not one encoder, but we have 2 or 3 encoders sitting in parallel. Okay. So, we have one encoder here, and let me draw another encoder here. Okay. So, there is another encoder here. Okay. This also has emitter, this also has receiver. So, these two are sitting on the same shaft and they are rotating, but they have some shift between them. Okay. What do I mean is, if I draw the side view, this is one emitter, this is one, and this is another one. Sorry. So, this is one encoder, it has slots like this. Okay. It is rotating about this. Behind that is another one which I have just drawn here. Okay. So, this one also has slots which are given like this. Now, you can see that there is a shift between this and that. So, they are not exactly aligned. So, if I say this is my encoder A and this is my encoder B, then encoder A will be getting signals when it is rotating and both are mounted on the same shaft. So, encoder A will be giving square wave forms like this, okay, whenever there is light and no light, light and no light. Now, encoder B, because it is slightly shifted, phase shifted. So, what would happen is it will be slightly delayed, the signal from B would be slightly delayed after A. Okay. So, what is done with both of these signals is that we use the XOR gate. So, we use XOR gate. Now, XOR gate basically means that if there is any change on any one signal, the second signal will change. Okay. So, what it does is, if you see here, the signal is going straight. So, this part is straight, there is a change there. So, immediately there is a change here. This is again constant, it is constant. Then the second signal, there is a change here. At this point, there is a second signal change right here. So, this comes down here, and again it is going straight, again this one comes down. So, there is again an up here. Okay. So, depending on any change here or here, there will be a change on my signal here. So, if you understand this, if this is clear, that basically this shows that using 2 encoders in parallel, we can increase the resolution of the system. You can see that the distance from here to here has only 1 square wave, whereas the distance from here to here now has 2 square waves. So, the resolution of the system has gone up. This is how in incremental encoders we increase the resolution of the system. Okay. So, this basically is explaining how an encoder works. This is very simple, and in 99% of our position measuring devices, we are using encoders. So, there will be a motor and there will be an encoder sitting at the back for measuring the position. Now, this encoder is giving us the position theta. Now, if you take the difference between two positions, theta say theta minus theta dash, you are getting del theta, which is your theta dot or velocity. and if you are getting twice, if you differentiate this theta minus del theta dash, then you are getting theta double dot. So, using the encoder we can also get velocity, we can also get acceleration. So, today we will stop here with position sensors, and in the next class we will continue with actuators and the other sensors. Thank you.